Hello everyone. This lecture is exclusively recorded for first year BSc student of BK College, Kalyan. This is calculus class, mathematics paper 1. In the last lecture, we have seen the characterization property of supremum and infimum. In this lecture, we will explore the supremum and infimum property on the sets. So before proving the properties of supremum and infimum on sets, let me state one of the important result for the bounded set. So a non-empty set S subset of R is bounded if and only if there exists a positive real number M which is positive such that when I say R plus, that means those x which are greater than 0 and x belongs to R, such that modulus of x is always less than equal to mod m, modulus of x less than equal to m for all x belongs to S. I will not be proving this property because this property, the proof of this theorem is mentioned in the notes which I have provided. So this is a homework theorem, but we will use this theorem extensively in coming properties. So now onwards, if I say a set is non-empty and if it is bounded, then I can straight away say that there exists a positive real number such that modulus of x is less than equal to m. You could see that when I say mod x less than equal to m, that means x is between minus m to m. So you could see that m is a upper bound and minus m is one of the lower bound. So when a set has lower bound as well as upper bound, then we call that set as bounded set, that is bounded above and bounded below. A set which is bounded above as well as bounded below is called as a bounded set. So now onwards, a boundedness can be replaced with this mathematical expression. So whenever I will say a set is bounded, that means I will say that there exists a positive real number such that the modulus of x is less than equal to m for every element belongs to set. Well, so with this property, we will use this property in upcoming theorem. So let me write down the results which I am going to prove now. So results: if capital A, comma capital B, comma capital S are non-empty, I don't need capital S anywhere. So are non-empty subsets of R, then number 1, if A is subset of B and B is bounded, then A is bounded. Second property which I supposed to prove: if A subset of B and B is bounded, then infimum of B is less than equal to infimum of A, which is less than equal to supremum of A, which is less than equal to supremum of B. The result number 2 is very interesting. So we will prove the results, we will see the how it takes this form. So this inequality will be clear in a proof. So let's prove the first one. First, let's prove this first one, and then we will go to the second. So proof of this. So what is given? It is given that A subset of B. Second thing, B is bounded. So when I say B is bounded, I can easily write down that there exists a positive real number M belongs to R plus such that mod x less than equal to M for every x belongs to B. Now in this case my set is B, hence I will say B. Okay, so and what I have to prove is as follows. I have to prove that A is bounded. So what I should say when will I say that A is bounded? I will say A is bounded provided mod x is less than equal to M for every x belongs to capital A. So if I could prove that, then I can straight away say that M is bounded. So the idea is you have to prove that A is bounded, then take any arbitrary element or any element from the set A. So let x belongs to A be an any arbitrary element. So that x will be any element. So it is basically representing my entire set A. So that can be taken any element from A. So if x belongs to A, that would imply x will definitely belongs to B. Why? Because A is fully contained in B, because A is a subset of B. That means A is fully contained in B. So whatever element A has, the same element B will have, moreover some extra element. So X will definitely belongs to B, but B is bounded. It is given that B is bounded. So that would imply there exists M belongs to R positive such that mod X less than equal to M. Right? So reason is since B is bounded. Now you can see that we started an element from A and we have shown that that element, arbitrary element, is less than equal to M. So this would imply for any x belongs to A, we have shown that there exists M belongs to R plus such that mod M, I should say mod x should be less than equal to M. So this would imply A is bounded set. Why it is bounded set? Because if you remember in a very first slide I said that if this is true, if M mod x less than M, then we said that set as bounded set. Right, here S is bounded, so now here we have shown it for the A. So this would imply A is bounded set. So well, the proof was not difficult. Now let me go for the second proof. What is given in the second proof? It is also it is given that A subset of B, also given that B is bounded, and I have to prove that infimum of B less than equal to infimum of A less than equal to supremum of A less than equal to supremum of B. So what I will prove? I will prove in a following case. I will show that first infimum of B is less than equal to infimum of A, and then I will show that supremum of A is less than equal to supremum of B, and then I will show that infimum of A is less than equal to supremum of A. So this three inequality I will have, and at last I will club all these three inequality, and I will say that infimum B less than equal to infimum A less than equal to supremum A less than equal to supremum B. But to prove this, one should guarantee that infimum of A, supremum of A, infimum of B and supremum of B exist. So existence of infimum and supremum of set A and B is very important. So their supremum and infimum exist because B is bounded. So B is bounded by order completeness property. We can say that infimum of B and infimum of A exist. Right. So since B is bounded by order completeness property of R, infimum of A, B, infimum of A, I should say B only. So order completeness property says that every bounded above set has supremum. And for the infimum we use basically this property also. So we can say that by order completeness property of R, infimum of B, infimum of supremum of, should say supremum of B exists and unique. Now we have talked about the set B, infimum and supremum of B. What about A? So A has a supremum and infimum only if A is bounded. Now you could see that A is bounded because A is a subset of B and B is bounded, so implies A is bounded. So also A is bounded. Why is bounded? Because just now we have proved. So by proof of 1, if you go through the proof 1, in proof 1 we shown that if A is a subset of B and if the B is bounded, then A is definitely going to be bounded. So again we can apply order completeness property. So by order completeness property of R, supremum of A, supremum of B, infimum of A, infimum of A and supremum of A. So I should say infimum of A exist and unique. So now it's very clear that sup A, sup B, infimum A, infimum B, they all exist. Right. So now I need to prove, now first I will prove that infimum of B is less than equal to infimum of A. So first we will put that infimum of what I have to prove. Let me write down infimum of B. This part I will prove first. Then I will prove this part, and at last I will prove the middle part. So this three inequality I will club it, and I will say that from 1 to 3 we will get this. So let's prove that infimum B less than equal to infimum A. Okay. So what I will do, I will start with an element from A. So let x belongs to A. If x belongs to A, then definitely x will belongs to B. The reason is since A is subset of B, so A is fully contained in B. So whatever element A has, the all element will automatically inherited in B also. So x belongs to B. but we know that B is bounded. I hope it is given in a statement only. Let's see. In statement have I given? Yeah, I said that A is subset of B and B is bounded. But B is bounded, so implies B has lower bound as well as upper bound. So we know that infimum is one of the lower bound and supremum is one of the upper bound, because when we have defined infimum and supremum, so infimum is always a lower bound and supremum is always a upper bound. Moreover, they has a special property. If it is infimum, then among all the lower bound, it is the greatest lower bound. If it is supremum, then among all the upper bound, it is the least upper bound. So when we say B has a lower bound, so infimum of B is a one of the lower bound, right? So this would imply infimum of B is lower bound, right? So we have seen that x less than equal to B. So what I will do instead of writing this, so I am not concerned about upper bound now. I will only go for the lower bound. So even I will not write this, because that this second part I will use it in a second part. So B has lower bound. So when I say B has a lower bound, then infimum B is one of the lower bound, and x less than equal to B, or x belongs to B. Write down this. So B has lower bound, so infimum B is lower bound. So x belongs to B, then there definitely infimum of B is infimum of B is definitely less than equal to x, because infimum of B is a lower bound and x belongs to B. So when we say x belongs to B, then it is always a lower bound is always smaller than any element from the set. So infimum of B is less than equal to x. But where does x belongs? We have started that x belongs to A. For every x belongs to A. Why I say every x? Because we have started a random or arbitrary x. So when we say random or arbitrary, that means it is true for any x belongs to A. So infimum of B is less than equal to x for all x belongs to A. This would imply infimum of B is lower bound of A. Now you can see that infimum B is always smaller than any element of x. So that element must called as a lower bound of A. But we already know one of the lower bound of A, but infimum of A is greatest lower bound of A. So now here I got a two lower bound of A. The first lower bound is infimum B. A के दो lower bound है. One is infimum B and the second one is infimum A. Both are the lower bound of A, greatest lower bound of A. But infimum A is the greatest lower bound. So both are a lower bound, that's true. But infimum A is the greatest lower bound of A. So there must be a relation between infimum B and infimum A. So if infimum A is the greatest lower bound, then infimum A is greater than equal to infimum B. This would imply infimum B is less than equal to infimum A. I hope you must have understood this, why I have written this, again I would like to explain. There are two lower bound of set A. One is infimum B and one is infimum A. But infimum A is the greatest lower bound. Hence, infimum A is larger than infimum B. Now, on the similar line, we have to prove for the supremum. So, let x belongs to A again. That would imply x belongs to B. The reason is A is subset of B. That would imply, but supremum of B is lower bound of B. Why it is so? Because B is bounded. I should say lower bound, I should say upper bound. Because B is bounded set, it is mentioned. So this would imply x is always less than equal to supremum of B. One may ask the question, why I have written this? Because x belongs to B and B का upper bound supremum B है. So x will definitely less than equal to supremum B. So this is true for all x belongs to A. So this would imply supremum B is upper bound of A. Also, supremum of A is upper bound of A. So we got two upper bound for set A. One is supremum B and the another one is a supremum A. Both are upper bound of A, but supremum of A is the least upper bound. Among all the upper bound, it is the smallest upper bound. So this would imply, but supremum of A is least upper bound of A. That would imply, I must say that supremum A less than equal to supremum B. Supremum A less than equal to supremum B. Let me number this as 2. Now let me see what one I have shown, infimum B less than equal to infimum A. I have shown that supremum A less than equal to supremum B. Now let me go here, not here, in a very second slide. So you could see that this part I have done, this part also I have done. Now I have to prove that infimum A is less than equal to supremum A. Okay. So let x belongs to an A. That would imply x is definitely less than equal to upper bound. Upper bound of A is supremum of A. And x is definitely greater than equal to lower bound. Lower bound of A is infimum of B. That would imply x must lies between upper bound as well as lower bound. I should say here infimum A, which is less than equal to supremum A. So if I club 1, 2, 3, we can see that from 1, 2, 3, you can see that infimum A less than equal to supremum A less than equal to supremum B, and here it will be infimum B. right? If infimum be less than equal to here, yes, infimum be less than equal to, yeah, second one, third one. So this completes the proof. So that's not difficult, but I need little more understanding of supremum and infimum. Then second result, which I will be, if A comma B are bounded set, then prove that A union B and A intersection B are bounded. Well, I will not be proving this. The proof of this is purely based on this result. So if you have understood this result, you just have to use this result. You can easily prove. This proof is already given in the notes which I have provided. So you can refer the notes to prove this. So this could be again homework. So maybe in lectures we will discuss about the proof of this. Now the third one. So if A comma B are bounded set, then prove that first one, supremum of A union B is equal to maximum of sup A comma sup B. And second one, infimum of A union B is equal to minimum of infimum A comma infimum B. The both proofs goes in on a same line. They don't need much knowledge. Means I mean the properties which we have proved so far are enough to prove this. So we will prove this one by one. So let me prove the first one. Solution to first. So first of all, one should observe that A and B are bounded. If A and B are bounded, then A union B is also bounded. And when a set is bounded, so it is bounded above. If it is bounded above, implies by order completeness property, supremum of A, supremum of B exists, and supremum of A union B also exists. So let me write down that. So since A comma B comma A union B are bounded above set, so by order completeness property of R, supremum of A, supremum of B, supremum of A union B exist and unique. Right. So let me call, let capital M1 is equal to supremum of A, capital M2 is equal to supremum of B. Right, so let me call this capital A as supremum of A and capital B as supremum of B, and then I will call their maximum of sup A comma sup B, which is same as max of m1 comma m2. So this maximum I will call it as m, right? And now I will claim that m is equal to supremum of A union B. If I could prove that m is equal to supremum of A union B, then the proof is done. So I'm assuming that the maximum of m1 and m2 is m, and my task is to prove that m is equal to supremum of A union B. So before writing that, I just tell you that when m is a maximum of m1 comma m2, that means m1 is definitely greater than equal to m is definitely greater than equal to m1, and m is also greater than equal to m2. So let me call this as number 1. So we will prove that, to prove that m is equal to supremum of A union B. So I need to prove m is a supremum of A union B. That means I need to prove two facts. The fact number 1 is m should be upper bound of A union B, and second fact, if I take any upper bound of A union B, then m should be smaller than that upper bound. So that is to prove that the first one, m is upper bound of A union B, and second fact, if k is any upper bound of A union B, then my m must be smaller than that k. So I need to prove these two properties. Right. So we'll prove one by one. They are not difficult to prove. So let's prove m is the upper bound of A union B. Proof. So let x belongs to A union B. So I will start an arbitrary element from A union B. Right. So this would imply, so either x belongs to A or x belongs to B. So this would imply x belongs to A or x belongs to B. So if x belongs to A, so let me have a partition of this. So one of the statement will be true, either x belongs to A or x belongs to B. So let me explore the both the cases. In both the cases I should see. So if x belongs to A, so if x belongs to A, that means x is definitely less than equal to supremum of A, because A is bounded, which is my capital M, capital M1. But capital M1 is already less than equal to M from 1. Right. So because one says that M is greater than equal to M1. So for any x belongs to A union B, my x is always less than equal to M. So this would imply for any x belongs to A union, let me say that instead of this, from this I will say that M is the upper bound of A union B. Now case 2, if A belongs to B, if x belongs to B, that would imply x less than equal to supremum of B, which is equal to M2, and again it is less than equal to M from 1. So you could see that for any x belongs to A union B, this would imply x is always less than equal to M. This would imply M is upper bound of A union B. So we have proved the part 1. So let me call this as star. Now double star statement will be if k is any upper bound, then I should say k m is less than equal to k. That will be my double star statement, and from star double star I will say that m is least upper bound of A union B. So let me go ahead now. So if capital K is any upper bound of A union B, right? So let x belongs to A. That would imply x will belongs to A union B. That would imply x is definitely less than equal to k. Reason is since k is upper bound of A union B. So what I got, if any x belongs to A, then x is less than equal to k. So this would imply k is upper bound of A. Also we know that m1, which is equal to supremum of A, is upper bound of A. So I got two upper bound of A. One is k and another one is m1. So this would imply m1 must be less than equal to k. Right. So let me call this as some another expression. So let me call it as Roman 1. Now if x belongs to A, then I got this. So if x belongs to B, then again I can say that x belongs to A union B. That would imply x is less than equal to k. The reason is since k is upper bound of A union B, right? So this would imply k is upper bound of B. This would imply but m2, which is equal to supremum of, have I said same one? Yeah, supremum of B is upper bound of B. So I got two upper bound for B. One is k and another one is m2. But m2 is the least upper bound, so m2 is less than equal to k. This is Roman 2. So m1 is less than equal to k, capital M2 is less than equal to k. So this would imply from 1 and 2, we can say that maximum of, I should say capital m1 comma m2 is less than equal to k. So whatever, this maximum will be either m1 or m2. But maximum of m1 comma m2, we have said somewhere, I have remembered, we have said that m is a maximum of m1 comma m2. So what I got is as follows. This would imply m is less than equal to k. Let me call it as double star. And if you remember, in a star I have said m is a upper bound. And now to prove second step, what I did, I have started k as a any upper bound, and I have shown that m is less than equal to k. So this would imply, so from star and double star, I can say that m is supremum, that is least upper bound of A union B. M is supremum of A union B. But what is M? M is nothing but maximum, which is, but because we have seen, we have written on a slide number 13, I have written M is equal to maximum of M1 comma M2. So hence maximum of M1 is nothing but supremum of A comma supremum of B. This is equal to supremum of A union B. So I hope this theorem you must have understood. If you did not understand, then definitely we have a scope to write down the same theorem. Yeah, we will ask the question related to this theorem in a tomorrow's lecture, that is on a Friday. But hope you must have understood. Now I thought to do minimum part also infimum, but I think I have gone beyond half an hour, so maybe I won't go beyond half an hour, because then I don't feel to go beyond half an hour timing, so it's okay. So the other part which I'm just searching that slide, just give me some time. Yeah, so this I have done, so this I will keep it as an homework. You try to do it. If you cannot, if you are unable to do it, then we will discuss this in a class. So this number one is a motivation to do the second one. So I hope that with the help of one, you can able to do it. The infimum of A union B is equal to minimum of infimum A comma infimum B. So that we will do in a lecture. You just try at your level first. If you could not, then we will definitely discuss this in a class. So thank you.